This is a presentation of our ENPH 459 project on the acoustic characterization of instruments using a circular microphone array. The goal of this project is to construct a system that can characterize string instrument radiation. The characterization that we are mostly interested in producing is a source map of the instrument soundboard. A source map is an image that indicates the location of sound sources over a plane. By making this plane the instrument soundboard, we can determine which parts of the instrument are responsible for radiating sound at various frequencies. Previous work done in obtaining these source maps includes an ENPH 479 project group that used a spherical microphone antenna to perform sound source localization over a plane, as well as a French research group headed by Jean-Louis Lecaroux that used a circular microphone array to produce source maps of a harp soundboard. Our project will consist of first building an array to measure instrument radiation data, then constructing an analysis algorithm that can use this data to produce source maps. In order to collect the data for characterizing an instrument, we need to build a rig that can measure the acoustic radiation in a circle around the instrument. 32 microphones have been provided by our project sponsor for this purpose. Our task is to use these microphones to build a circular microphone array that can fully encircle a string instrument. The requirements that our array design must satisfy are as follows. We must have the 32 microphones evenly spaced over an approximately 2-meter diameter circle. The array must be lightweight and maneuverable in order to be moved in and out of the anechoic chamber with relative ease. The microphones must be attached in such a way as to allow their easy removal. This will help us during transport and will allow for easy replacement of broken microphones. In order to hold the instrument inside the array, an instrument frame must also be designed. In order to reduce frame vibration, the frame must not be stiffly coupled to the instrument. The frame must also be made in such a way as to allow variation in the relative orientation between the frame and the instrument. For our array design, we decided on a single-piece circular array that would be hung from the roof. The main structure of the array will be provided by a 6-foot diameter hula hoop that is supported by a square steel frame. The steel frame was added in order to eliminate the warping of the flimsy hula hoop. The microphones will be fastened to the hoop using interlinked hose clamps and zap straps. The zap straps fit around a groove in the microphone casing, allowing the microphones to be easily snapped in and out. The frame will be mounted to a 1-inch rod in the anechoic chamber ceiling with a small pipe clamp. The pipe clamp is tightened with a small lever, allowing for quick attachment and removal of the frame from the ceiling. This design is stable, lightweight, and easy to manufacture, effectively satisfying our initial design criteria. To hold the instrument inside our array, an instrument frame was built out of 80-20 aluminum extrusions. The instrument will be held inside a simple rectangular frame. To ensure a vibration isolating connection, the instrument is held in the frame using bungee cords and elastic bands. The frame can be mounted either vertically, with the instrument hung from its neck, or horizontally, with the instrument hung from the string's end neck. The frame can be rotated around its support axis and can be fixed at one of 16 designated angles using a plexiglass guide. With our array built, we begin measuring instrument radiation. The instrument we used for this first measurement is a North African oud. This lute-like instrument has already been thoroughly characterized by our sponsor, allowing us to verify our results to previous work. The general measurement procedure is to strike the instrument near the bridge and record the sound produced. This measurement will be made over various instrument orientations as needed. For conducting these measurements, the following equipment is used: our microphone array and instrument frame, an automated impact hammer, a data acquisition system, and a computer with LabVIEW. The automated impact hammer consists of a small DC motor connected to an aluminum hammer. The hammer is triggered by an external function generator. The data acquisition system we use can sample 32 mono inputs at rates of up to 40 kHz, outputting the results to the computer. The computer in the lab has been modified to receive the DAC signals and uses a LabVIEW program to write the data to file. The first step in taking a set of measurements is to position the instrument and impact hammer within the frame. For the soundboard source map data, the instrument is oriented vertically in the hoop, with the impact hammer striking horizontally. The instrument is placed so that the soundboard of the instrument lies in the hoop plane. With the instrument and hammer in place, we now trigger the impact hammer. The impact hammer strikes a point on the soundboard just above the bridge, causing the instrument to resonate. The microphone data is then recorded by the computer, which records for half a second at 10 kHz and writes the results to the file for analysis.
Using the equation for a monopole sound source, we were able to generate simulated data for our circular microphone array in order to characterize its sound source localization capabilities. Here R is the distance from the monopole and A is the wave amplitude. In this graph, each wave represents the input to a single microphone for a simulated monopole sound source. The amplitude is lower for microphones that are further from the monopole. We use this simulated data as input to our sum and delay beamforming algorithm and experimented with changing the frequency and location of the sound source. The following animation depicts the sum and delay beamforming algorithm process. The red arrows represent the phase and amplitudes of the signals at each microphone when they are delayed based on the distance that they would have to travel to reach that microphone from the supposed location of the sound source. The black arrow is the sum of all the delayed microphone signals. At the center, where the monopole is located, all the red arrows are aligned, which results in a maximum amplitude for the black arrow. In this first demonstration, we show how the source map changes for a monopole as it spirals out from the origin. Notice how the distance between the red region, which is the main lobe, and the black dot, which is the monopole, increases. For our second demonstration, we will leave the monopole at the origin and increase its frequency. Notice how it looks as though we are zooming out due to decreasing wavelength. When the wavelength is less than half the distance between the microphones, spatial aliasing occurs, as indicated by the onset of ridges. Our sampling rate is 40 kHz, therefore, the Nyquist frequency is outside of the auditory range. Here we show two monopoles separating, which illustrates the inability to directly determine the locations of multiple sources. Also, we have taken snapshots from the previous demonstration with two different microphone configurations. The random configuration results in much worse source maps, and when we increase the number of regularly spaced microphones, there is little improvement. Our first test to demonstrate the functioning of our microphone array was to determine the location of a monochromatic sound source. In this image, the source map is overlaid on top of a photo of the sound source, and here we show the position of the main lobe, which is accurate to within 2 centimeters. The instrument's sound decays over time, therefore we had to determine a valid window of time for which to use the data. This next animation depicts the effect that this time window has on the beamforming output. As can be seen in the graph, the output averages out over time and the results improve. Here we show the source map of the oud for one of its major resonances, along with a photo of the actual measurement setup. In this next animation, we will show the beamforming output for this measurement configuration as the frequency is swept across the entire spectrum. There's a lot of information contained here, and it serves to show the complexity of the instrument's radiation. Note that this animation will be different for each instrument and can be used by someone with a trained eye to instantly characterize the radiation produced by an instrument. In regions where the oud does not radiate as strongly, the signal-to-noise ratio decreases and the output becomes random, but in regions of high resonance, there are prolonged periods of coherence. Now we cut ahead to the higher frequency region to show the similarities with the simulated monopole from the previous demonstration. Note the rings with the ridges, which signify spatial aliasing. Applying nonlinear's least squares curve fitting to the problem of computing source locations by assuming that the sound sources could be represented by a distribution of monopoles was determined to be too inaccurate. For an unlimited frequency range, there are simply too many monopoles to fit for, as was demonstrated in the previous clip, and reducing the frequency range also introduces error. We had some success with guessing locations of the sound sources. For instance, the following two graphs show the source map for a major resonance of the oud at approximately 1150 Hz. Note that these two datasets were taken on separate days. By overlaying these graphs onto a picture of the measurement setup, we were able to hypothesize that for this resonance, the oud radiates with the most power from 2 points on either edge near the peaks in the source map. Here we see a source map for a simulated set of monopoles whose locations are indicated by the black dots. The general pattern is the same as for the oud data, which confirms our hypothesis. By decreasing the distance between the simulated monopoles, we again see the same pattern, but slightly altered, which shows how laborious the trial and error process can become when trying to obtain identical source maps using equivalent sources. The next step will be to automate this process of determining the equivalent sources. In the paper by Le Caroux, a method is outlined for using Tikhonov regularization to compute the output of the inverse of the transfer function from sound source to microphone input. We recommend the implementation of the Tikhonov regularization as a future project for engineering physics students.
In conclusion, over the course of our project, we designed and constructed a circular microphone array that satisfies all of the initial design requirements, and we designed, implemented, and tested a source mapping algorithm that has demonstrated success in mapping complex sound sources. Our array and code will be used for future work by our sponsor, including measuring the effect of sound post placement on viola sound, as well as characterizing the sound radiation of various Chinese string instruments. We leave you with a short clip of measurements being conducted on one such instrument, the guzheng.